Hello friends and welcome to another lecture on chemical engineering thermodynamics. Today we'll take up a question from Chemical Engineering Thermodynamics 1 paper from Mumbai University, May 19, and the question is 4b. The question is on your screen. Derive an expression for fugacity coefficient of ammonia vapor. Ammonia vapor obeys Redlich Kwong equation of state, and the Redlich Kwong equation of state is given to you. Now, how do we attack this derivation? It's for 10 marks. So if a few fundamentals are understood, the derivation is quite simple. I will start with a few fundamentals, and these need not be written in the answer book. I will indicate from where we can start. But why I'm starting from the fundamentals is because you need to understand where does the starting equation come from, so that you have a better idea to appreciate that how the integrals are being performed, right? So we all know that from the first law. Of course, we all know that from the first law that du is equal to dq minus p into dv. Now, if we add dpv on both the sides of this equation and subtract dts from both sides of this equation, that is the first law, we get dg is equal to minus s dt plus v tp, right? Where g, as we are aware, is defined as h minus ts, right? So if we take the above equation at constant temperature, we get dg is equal to v dp, right? And this is at constant temperature. Now, if we apply this to an ideal gas, so we get dg is equal to RT by P dP, which can be written as RT d ln of P. So we know that the change in Gibbs free energy for an ideal gas is going to be equal to RT into d ln of P. So this change is at constant temperature. For a real gas, we can say dG is equal to RT d ln F, where F is defined as fugacity. Now, this is a mathematical concept that gets introduced because for an ideal gas, if we have pressure P, then we replace it by a number, fugacity, right? And we say that the change in Gibbs free energy of a non-ideal gas or a real gas is dG is equal to RT d ln of F. Now, it goes without saying that if the gas behaves as an ideal gas, then F for the gas is equal to P. For the ideal gas, F is equal to P. Now, this is for real gas, right? Now, there is one more concept introduced here. That is, we take the difference of equation number 1 and equation number 2. So we take 2 minus 1. So we get dg minus g ideal gas is equal to RT d ln of F over P. Now this is written as RT d ln of phi, where phi is defined as the fugacity coefficient. Okay, so phi is defined as the fugacity coefficient, and it is clear that fugacity coefficient is f by p. And the RHS, that is the LHS, not the RHS, the LHS gets defined as G residual. G residual is nothing but d G minus G ideal gas. Okay, so now what we have is d G residual by RT. Since all this derivation that we have done is at a constant temperature, so we can take RT on the LHS in the denominator and we write it as d ln of phi, right? Now let's have a look at the LHS of the equation if we want to find out the fugacity coefficient. Now let's turn it over and that gets interesting, and we get 1 over RT dg minus dg ideal gas, and we can write it as 1 over RT. Now dg is VdP for a real gas minus V ideal gas dP. So this is V minus V ideal gas over RT dP is d ln phi. So this is the starting point of our expression for calculation of fugacity. This is our starting point. Well, all this derivation that was done before this was only to explain you this concept. Okay, and now you would very well appreciate that all this is at constant temperature. So I will not stress on this point. It is understood that all the integration and differentiation that I do, the temperature remains constant during all that operation, right? Now what we can say is, what we have now is, we'll choose a different color. So we have d ln of phi is equal to 1 over RT V dP minus V ideal gas dP. So VdP, writing V explicitly in terms of pressure and temperature is not possible for a cubic equation of state like a Redlich Kwong equation of state that we have been given. So here we can do the modification, 1 over RT, and VdP can be written as dPV minus P dV, and this can be written as V ideal gas dP. Now let's only take the RHS part of the equation and deal with it. So for the RHS part, we can write it as dPV by RT minus P over RT dV minus V ideal gas over RT dP. Now P is equal to RT V minus B minus A upon root T V plus B for a Soviet-Redlich Kwong gas, or a gas that obeys Soviet-Redlich Kwong equation of state. So the RHS can be written now as dz, where we all know that Z is equal to PV over RT for a real gas, and Z is equal to 1 in case it's an ideal gas. Then afterwards what we have is minus. So we go ahead with the second term and start modifying it. So therefore we get dV over V minus B plus A dV upon root T V plus B minus V ideal gas by RT dP. Don't worry, all of this is going to get simplified. So what we have now in RHS is dz, and we have minus dV over V minus B, and we can write this particular expression as we missed an RT here. Okay, so this is RT multiplied by the above. We missed an RT here because this gets divided by RT. Okay, so plus A over RT root of T B, and then we can write down this as dV by V minus dV upon V plus B minus V ideal gas by RT dP. And all of this further now simplifies to, so we make a few, define a few constants here. We could define A as AP by root T RT square, and we define B as BP by RT. So the RHS now is equal to dz minus dV upon V minus B plus A over B, and we get this as dV by V minus dV upon V plus B, and finally we get this as V ideal gas can be written as RT over P, and we have an RT here too, and the RT and RT gets cancelled out, and we have dP here. So the last term can be written as d ln of P. Now see, we have simplified it quite well. So we have the expression of LHS and RHS together as d ln of phi is equal to dz minus dV upon V minus B plus A upon B, and you have dV over V minus dV over V plus B minus d ln of P. Now, the most important point here is to understand how we do the integration. What are the limits of integration here? Well, the limits of integration here are, we integrate from the condition where at P the gas is an ideal gas to the condition where the gas is a real gas. Okay, at real gas conditions, okay, at P, okay, at P, the real gas condition. Now, here, what are going to be the limits of phi? At the ideal gas condition, what we have is, as we have explained it before, for an ideal gas, F is equal to P. So what we are going to have is, for this condition, we are going to have phi is equal to 1 because F is equal to P. And for this condition, we are going to have phi is equal to F over P. So we can integrate the LHS from a condition of an ideal gas to a condition of real gas and d ln of phi. This is going to be equal to integral dz from a condition of ideal gas. So for an ideal gas z is 1, for a real gas z is equal to z minus dv over v minus b. So it's going to be v ideal gas to v, the real gas volume, plus a by b integral v ideal gas v dv over v minus integral v ideal gas v dv over v plus b. And please note the last one is very important here to understand. The limits of integral are going to be from pressure P to pressure P, and this is going to be d ln of P. Remember one thing, we are only integrating from a condition of the gas behaving as an ideal gas at pressure P and temperature T to the condition where the gas behaves as a real gas at pressure P and temperature T. The pressure does not change. We only take it from an ideal gas to a non-ideal gas condition. And therefore, the last term here is going to be 0. Now what we get is ln of phi z minus 1 minus ln of v minus b over v ideal gas minus b. Okay. Now here you will not have b because b is 0. Remember one thing, b is 0 for an ideal gas, plus a over b. Now this is going to be ln of v over v ideal gas minus ln of v plus b over v ideal gas. Remember, b will not come here. The reason being, for an ideal gas, b is 0. And therefore, we get ln phi as z minus 1, right? ln. Now, v minus b can be written as z RT by p minus b, and v ideal gas can be written as RT by p plus a over b. Now, the lower limit, that is v ideal gas and v ideal gas, it will get cancelled here, and you get this expression as ln v over v plus b. right? And this V over V plus B can be written as ln of V can be written as Z R T by P, and this can be written as Z R T by P plus B. Now we have a very neat little expression in Z, which is nothing but Z minus 1 minus ln of Z minus B, because we remove RT by P common, and we also know that B is equal to BP over RT. We have already defined this, plus A over B, and finally we have this as Z over Z plus B. So we have our expression for the fugacity of a van der Waals gas. Now remember, whenever we do any derivation, we should test it for the conditions. So if the gas is an ideal gas, right, then for ideal gas we have Z is equal to 1, and for ideal gas, needless to say, B is equal to 0. Now what do we get ln phi in this case? In this case, we will get ln phi is equal to 1 minus 1 minus ln of 1 minus 0, and the last expression, that is A by B ln Z, Z plus B, this is going to be equal to 0. That is because A is 0 and B is 0 for an ideal gas. And what do we get finally here? We get is it as minus ln of 1, right? We get it as minus ln of 1. So this is 0, this is 0, and this is minus ln of 1. And what do we get from this? We get from this minus ln of 1. Now this is going to be equal to 0, right? Minus ln of 1. So ln of 1 is 0, and finally minus 0, well, that's 0. And then we can write this as ln phi is equal to ln of 1. Right? I could have always taken the minus 1 and raised 1 to the power of minus 1 and written it as ln 1 and proved it mathematically that way. Well, it's the way you look at things, which automatically means here that phi is equal to 1 and f by p is equal to 1, or f is equal to p. And we already have shown that this is true if the gas behaves as an ideal gas. For an ideal gas, the fugacity is equal to the pressure. Therefore, the expression that we have got is the correct one, right? So we can be very sure that the expression that we have derived is fully correct, and we should be getting full credit for that, right? So when you are solving it in the examination, right, you have to start from this point. So this is the point where you are going to start it off. And this is the point where you are going to end it all, right? So this is the point where you're going to end it all. And a simple straightforward derivation like this for 10 marks, I think, is justified, and one can easily score 10 marks in this. But what happens is most of the students, they do not mention the conditions of integration, or they are not aware of the condition of integration. They do not explain it well, and therefore what happens is teachers tend to cut the marks, because you cannot mechanically do something and just show that this is the derivation. You have to explain. Whenever you're doing a calculus derivation, you have to explain the limits, why you have taken the limits the way they are taken, and this is important, right? So keep watching for more such videos, and do subscribe. That's a very good motivation to me. Your subscription, your views are a very good motivation to me to make such videos. Keep watching. Have a great day. Bye.